In this video, we will look at elements that require special processing in nodal analysis. The first special case that we will consider are grounded voltage sources. And it does not matter if the grounded voltage source is an independent source or a dependent source, both of them are handled the same way. The circuit shown has 4 nodes, and we have selected node D as the reference node or the ground node where the voltage will be 0 volts. The circuit also contains 2 independent voltage sources, and one end of each of these sources is connected to the reference node D. These 2 sources are called grounded voltage sources because they have one node which is common with the reference node. It does not matter whether the positive end or the negative end of the voltage source is connected to the reference node. What is important is that any one of these nodes is connected to the reference node. Recall that for nodal analysis, we have to write KCL equations in terms of the known element values, and the unknown values are the nodal voltages VA, VB, and VC. Also recall that a voltage source can supply an arbitrary amount of current, and it depends on what else is connected to the voltage source. We have to keep all of this background knowledge in our mind as we try to write nodal equations for the circuit shown. Consider what happens if we try to write KCL equations at node A, which is connected to a grounded voltage source. Following the passive sign convention, the current through the voltage source is as shown, and the current through the resistor can be arbitrary, and we will choose the direction as shown. Since the voltage source can conduct an arbitrary amount of current, we are unable to write KCL at node A in terms of the unknown values, which are VA, VB, and VC, and any other element values which are known. Also note, since the voltage source is connected between nodes A and D, the voltage at node A, VA, will be simply 2 volts because of the voltage source. Since we know the nodal voltage VA and we cannot write a KCL at node A, we can ignore this node when we are considering nodal analysis, and we will put a cross through node A to indicate that we are not going to consider this node in nodal analysis. Similarly, if we consider node C, which is also connected to a grounded voltage source, we know the voltage at node C is equal to 4 volts, and we cannot write a KCL at node C because of the grounded voltage source, and we will also put a cross through this node to indicate that we do not have to worry about this node in nodal analysis. This will leave only node B, at which we will write a KCL. We will take that all currents are leaving node B through the 3 resistors in the direction shown, and KCL at node B will give the current leaving through the 2 ohm resistor will be VB minus VA over 2, plus the current leaving through the 4 ohm resistor, VB over 4, plus the current leaving through the 1 ohm resistor, VB minus VC over 1. This must be equal to 0 to satisfy KCL. Substituting known values for VA and VC, we will get VB minus 2 over 2 plus VB over 4 plus VB minus 4 over 1 is equal to 0. This is one equation in one unknown, and we can solve for VB is equal to 20 over 7 volts. We have solved for all the nodal voltages VA, VB, and VC, and the solution of this circuit is complete. Once all the nodal voltages are known, we can calculate any other current or voltage in the circuit. For example, we can calculate the current through the 2 volt source by writing KCL at A. If we denote the current through the source as IS and the current through the 2 ohm resistor as I2, then we have I2 plus IS is equal to 0, or IS is equal to minus I2 is equal to minus of VA minus VB divided by 2, and substituting for the nodal voltages will give us minus of 2 minus 20 by 7 divided by 2, which will be equal to 3 by 14 amperes. Therefore, it was only at the initial steps that we could not write a KCL at node A because the current through the voltage source was arbitrary. However, once we know all the nodal voltages, we can calculate the current through the voltage source by keeping the source current as unknown and using the nodal voltages and other element values to write a KCL at node A. To summarize, grounded voltage sources require special processing in nodal analysis. Since one end of the voltage source is connected to the reference node, we know the voltage at the other end, and we know one of the nodal voltages because of this voltage source. We do not write KCL equations at the node connected to a grounded voltage source because of two reasons. The first reason is that the voltage source can provide an arbitrary amount of current, and we cannot write a KCL in terms of the nodal voltages and other known element values. And the second reason is that since we know the nodal voltage, we do not need to write a KCL at this node. Thus, grounded voltage sources will reduce the number of equations and the unknowns that are required for nodal analysis.